Section 702.5 of the National Electrical Code addresses the capacity of optional standby systems. It states that optional standby systems shall be capable of supplying selected lighting and receptacle outlets for essential equipment. The key takeaway is that the optional standby system, typically a generator set, does not necessarily need to power everything in the panel it feeds. Instead, its capacity should match the essential equipment connected to selected lighting and receptacle outlets. The owner or operator of the system has the authority to designate which lighting and receptacle outlets are considered essential. This selection process, determining what constitutes essential equipment, can occur either during the initial installation phase or during the ongoing operation of the system. To effectively size a generator for an optional standby system, one must first identify the essential load requirements of the building or facility. These requirements will vary depending on the specific application. Some common examples of essential loads include, firstly, lighting for egress paths, ensuring safe evacuation during a power outage. Secondly, lighting for critical areas, such as operating rooms in a hospital or server rooms in a data center, where continuous operation is paramount. Thirdly, receptacles for essential equipment, which could include medical equipment, computers, or other devices vital to the function of the facility. Fourthly, heating, ventilation, and air conditioning or HVAC systems, particularly in climates where temperature control is crucial for comfort, safety, or equipment operation. Fifthly, fire protection systems, ensuring that fire alarms, sprinkler systems, and other life safety equipment remain operational. And sixthly, security systems, maintaining surveillance, access control, and other security measures. Once the essential load requirements are identified, the generator can be sized accordingly. The generator's capacity must be sufficient to supply these essential loads for the expected duration of a power outage. It is critical to avoid oversizing or undersizing the generator. An oversized generator will be more expensive to purchase and maintain, and it may operate inefficiently at lower loads. An undersized generator will be unable to supply the essential loads, defeating the purpose of the standby system. The selection of essential loads should be carefully documented and communicated to the owner or operator of the system. This documentation should include a list of the selected lighting and receptacle outlets, as well as the essential equipment that is connected to them. It is also important to provide training to the owner or operator on how to operate the system and how to manage the loads during a power outage. This training should cover topics such as starting and stopping the generator, switching between normal power and generator power, and monitoring the generator's performance. Understanding the electrical characteristics of the loads is crucial for proper generator sizing. Firstly, determine the power requirements of each essential load. This information is typically found on the equipment's nameplate. Nameplate information includes voltage, amperage, and power factor. Voltage is the electrical potential difference, measured in volts, required for the equipment to operate. Amperage is the electrical current, measured in amps, that the equipment draws during operation. Power factor is a measure of how efficiently the equipment uses electrical power. Secondly, calculate the total power requirements of all essential loads. This is done by summing the power requirements of each individual load. Consider both the continuous load and the inrush current. Continuous load is the steady-state power consumption of the equipment. Inrush current is the momentary surge of current that the equipment draws when it is first turned on. The generator must be able to handle both the continuous load and the inrush current. Thirdly, apply a safety factor. It is generally recommended to add a safety factor of 20 to 25% to the total power requirements. This safety factor provides a buffer to account for any unexpected load increases or variations in generator performance. Fourthly, select a generator with a capacity that meets the calculated power requirements, including the safety factor. Generators are typically rated in kilowatts or kilovolt amperes. Kilowatts is a measure of the real power that the generator can supply. Kilovolt amperes is a measure of the apparent power that the generator can supply. The power factor of the loads will determine the relationship between kilowatts and kilovolt amperes. Fifthly, consider the generator's fuel source and runtime requirements. Generators can be powered by a variety of fuel sources, including gasoline, diesel, natural gas, and propane. The choice of fuel source will depend on factors such as availability, cost, and environmental considerations. The runtime requirements will depend on the expected duration of power outages. It is important to select a generator with a fuel tank capacity that is sufficient to provide the required runtime. Sixthly, ensure that the generator installation complies with all applicable codes and standards. The National Electrical Code, or NEC, provides detailed requirements for the installation of generators. It is important to consult with a qualified electrician or engineer to ensure that the installation meets all applicable requirements. In addition to sizing the generator, it is also important to select the appropriate transfer switch. The transfer switch is a device that automatically switches the building's electrical system from normal power to generator power during a power outage. There are two main types of transfer switches: automatic transfer switches or ATS and manual transfer switches or MTS. Automatic transfer switches automatically switch to generator power when a power outage is detected. Manual transfer switches require a person to manually switch to generator power. Automatic transfer switches are typically used in applications where continuous power is critical, such as hospitals and data centers. Manual transfer switches are typically used in residential and small commercial applications. The selection of the transfer switch will depend on the specific needs of the application. Consider the following factors when selecting a transfer switch. Firstly, the amperage rating of the transfer switch must be sufficient to handle the total current of the essential loads. Secondly, the voltage rating of the transfer switch must match the voltage of the electrical system. Thirdly, the transfer switch must be listed by a qualified testing laboratory, such as Underwriters Laboratories or UL. Fourthly, the transfer switch must comply with all applicable codes and standards. Understanding the different types of loads connected to the generator is important. Firstly, resistive loads, like incandescent lights or heaters, draw current that is in phase with the voltage. Secondly, inductive loads, such as motors and transformers, draw current that lags behind the voltage. Thirdly, capacitive loads, such as capacitors and some electronic devices, draw current that leads the voltage. The power factor of the load is a measure of the phase difference between the voltage and current. A power factor of 1.0 indicates a purely resistive load, while a power factor of less than 1.0 indicates a reactive load, either inductive or capacitive. Generators are typically rated in kilovolt amperes because this takes into account both the real power in kilowatts and the reactive power in kilovolt amperes reactive. The generator must be able to supply both the real and reactive power requirements of the loads. Motor starting can be a significant challenge for generators. When a motor starts, it draws a large inrush current that can be several times its normal running current. This inrush current can cause a voltage dip, which can affect the performance of other equipment connected to the generator. To mitigate the effects of motor starting, several techniques can be used. Firstly, using a soft starter, which gradually increases the voltage applied to the motor, reducing the inrush current. Secondly, using a variable frequency drive, which controls the motor's speed and torque, further reducing the inrush current. Thirdly, oversizing the generator to provide sufficient capacity to handle the inrush current. Fourthly, using a generator with a high short circuit capability. Regular maintenance is essential for ensuring the reliable operation of the generator. This maintenance should include, firstly, regular inspections to check for any signs of damage or wear. Secondly, oil changes to maintain proper lubrication of the engine. Thirdly, filter replacements to ensure clean air and fuel. Fourthly, battery maintenance to ensure reliable starting. Fifthly, load testing to verify the generator's capacity and performance. It is also important to keep accurate records of all maintenance activities. Optional standby systems provide a valuable source of backup power during power outages. By carefully sizing the generator and selecting the appropriate essential loads, one can ensure that critical equipment continues to operate, minimizing disruption and maximizing safety. Remember to always consult with qualified professionals for installation and maintenance of these systems. This ensures adherence to local codes, safe operation, and optimal performance of the backup power system. This includes, but is not limited to, proper ventilation for the generator to prevent carbon monoxide buildup, grounding to prevent electrical hazards, and adequate fire suppression systems in the generator room. It is also essential to have a clear and well-documented plan for operating the generator during a power outage, including procedures for starting and stopping the generator, switching between normal and backup power, and monitoring the system's performance. This plan should be readily available to all personnel who are responsible for operating the generator. Proper training is crucial for ensuring that personnel are able to safely and effectively operate the generator during a power outage. This training should cover all aspects of generator operation, including starting and stopping the generator, switching between normal and backup power, monitoring the system's performance, and troubleshooting common problems. Regular drills and simulations can help to reinforce training and ensure that personnel are prepared to respond effectively to a power outage. Optional standby systems are becoming increasingly common in a variety of applications, including residential, commercial, and industrial settings. As the reliance on electricity continues to grow, the importance of having a reliable source of backup power will only increase. By understanding the principles of generator sizing and essential load selection, one can ensure that the optional standby system provides the necessary power to keep critical equipment operating during a power outage. Continuous monitoring of the generator's performance is crucial for identifying potential problems early on. This monitoring can be done manually or automatically, using a variety of sensors and monitoring systems. Key parameters to monitor include voltage, current, frequency, power factor, and fuel level. Any deviations from normal operating parameters should be investigated and addressed promptly. Remote monitoring capabilities allow for real-time monitoring of the generator's performance from any location. This can be particularly useful for facilities that are remotely located or that have limited on-site personnel. Remote monitoring systems can also provide alerts and notifications when problems are detected, allowing for proactive maintenance and preventing potential downtime. The integration of the generator with the building's automation system allows for seamless and automated operation of the standby system. This integration can include automatic starting and stopping of the generator, automatic switching between normal and backup power, and automatic load shedding to prevent overloading the generator. Building automation systems can also provide valuable data on the generator's performance, which can be used to optimize its operation and improve its reliability. In conclusion, the proper sizing and operation of optional standby systems are essential for ensuring a reliable source of backup power during power outages. By understanding the principles outlined, one can ensure that the standby system provides the necessary power to keep critical equipment operating, minimizing disruption and maximizing safety.